Morning, everyone. My name is Justin Moran, with the Head of Public Affairs with Wind Energy Ireland. Apologies for having a couple of small technical problems this morning, but hopefully you should be able to see the slide there at the beginning, Endgame for fossil fuels. I would like to thank you for joining us today and I suppose participating in what we think is going to be a very exciting webinar that will be looking at how we can get to a situation when by 2030 we can be under 2 million tons of CO2 from the electricity sector, and going beyond that, how we can get to a situation where we can have a zero carbon electricity system in Ireland. I'm just going to briefly go through the agenda for the webinar. We're going to be joined by our CEO, Noel Caniff, who will be introducing the background to this piece of research and why we carried it out, and the research that we've done that has led up to the situation where we have Endgame. Then Dr. Mark Turner will bring us through the main presentation, and following that we'll have an opportunity for questions and answers. The slides from the presentation and the link recording the webinar, including my slightly inept opening and the technical difficulties we had at the start, will be made available after this session and will be sent to all registered attendees. So I'm just going to hand over now to Noel, and he's just going to take us through the background to the research.
Good morning, everybody, and thank you very much, Justin, for the introduction. Delighted to have you all here this morning at a very exciting time for our industry, and delighted to introduce you to our newest flagship report, Endgame, a zero carbon electricity plan for Ireland. To give people some background on this, in 2018, Wind Energy Ireland, or IWEA at the time, worked with Baringa partners to publish the 70 by 30 report, which was a landmark report at the time and set the scene for setting a target of 70% renewable electricity for the power system by 2030. This was then brought into government policy through the Climate Action Plan, which was published in June 2019. Since then, there's been a lot of exciting changes in terms of policy development, both from a government point of view and from new updates from system operators, from EirGrid and ESB, on how they intend to manage the network by 2030. This year, we thought it would be opportune to bring Baringa back to update the 70 by 30 report and bring it into 2021 by taking into account a lot of the updates and the changes that we've seen in policy since the 70 by 30 report in 2018. To give you an idea of some of those changes, in June 2019, the Climate Action Plan was published, which set the target for 70% renewable electricity. It also set in place capacity targets to deliver for onshore wind of 8.2 gigawatts by 2030 and offshore wind of 5 gigawatts by 2030. Following that, the programme for government was published last summer. That set in place a target to reduce Ireland's overall emissions by over 50% between now and 2030, moving from an emissions intensity or an emissions output in Ireland of around 60 million tonnes per year down to 30 million tonnes per year by 2030. In the electricity sector, we ourselves are responsible for around 10 million tonnes of CO2 each and every year. And with Endgame, we're going to show you how we can significantly reduce it. One of the other main changes that we saw since the 70 by 30 report was EirGrid's Shaping Our Electricity Future consultation, which took place earlier this year. That set out how EirGrid and Sony are aiming to operate the power system with 95% renewables at any point in time by 2030, an update on where we were at in 2018 in our 70 by 30 report. So over the last 7 months, we've worked with Mark Turner and Alec Granville in the team in Baringa to bring you the Endgame report. And I'm really excited to hand over to Mark now, and he'll talk you through how we believe we can reduce Ireland's electricity sector emissions by over 80% between now and 2030. Over to you, Mark.
Fantastic. Thanks very much, Noel. And I'm very excited to run through with you this morning the findings that we've produced in this study and in the Endgame report. And so, as Noel says, we started with our previous 70 by 30 study. We reflected the changes in the market since then. And the key conclusions from the study are in two parts. First of all, we looked at how Ireland could achieve a 2 million ton CO2 power system and how that might be achieved by 2030. And then in the second phase of the study, we went further and looked at what will be needed to completely eliminate power sector emissions. So let me take you through those step by step. First of all, in phase one, our report and our findings show that by 2030, Ireland can feasibly achieve a less than 2 million tonne of CO2 power sector. That's a reduction of around 80% on today's emissions, which are around the 9 to 10 million tonnes of CO2 level. The key message in our report is that Ireland can achieve that without the need for new or unproven interventions. That can be achieved simply by doing more of the types of interventions that are already envisaged today to meet the 70% target. This is using proven technologies and rolling out existing plans a little faster and going a little further. And that gets us to that 2 million tonnes of CO2 point. One of the key enablers of that outcome is the utilization of zero carbon system services. And this comes through very clearly in our study. There is a huge benefit to be gained in rolling out technologies such as battery storage and flywheels or synchronous compensators to provide reserve and system stability services instead of the gas-fired and fossil-fueled assets that are providing that today. I'll set out in a little while what the benefits are of that and how those benefits come through, but that is key to achieving that less than 2 million tonnes outcome. And those zero carbon system services are one of the keys to unlocking the delivery of the required renewable energy that gives that less than 2 million tonnes outcome, which is around 85% renewable power. That figure emerged from our analysis, so that wasn't a kind of a goal or target in itself. That emerged as what was required to get this sub 2 million tonnes outcome. Next slide then, please. I'm doing my Chris Whitty impersonation here this morning with the next slide, which is quite in vogue these days. So the key, if we just go back one, Justin, the key additional finding in phase one is that 2 million tonne CO2 outcome and the 85% renewables can be achieved at a lower cost to end consumers in Ireland compared to delivering the less ambitious 70 by 30 target. And again, I'll unpick exactly how that cost saving is derived in a little while, but an extraordinary message that this actually costs less overall than the less ambitious level. So then in the second phase of the work, we go further and we show how a zero carbon power system is possible in Ireland by 2030. And we believe this is very achievable as a target for the 2030s. What we find is that a viable pathway to get to a zero carbon power system does require investment in additional technologies over and above what we're doing for the less than 2 million tonne case. And there are a couple of key technologies that emerged in our study. Number one is long duration storage, the bulk shifting of energy from periods when you have excess renewable generation, and then using that energy in periods when you would otherwise have to use gas-fired generation. So long duration storage, and alongside that, green hydrogen, which itself can act as a form of long duration storage. Again, utilizing wind and solar during periods when there's plenty available to generate hydrogen, using that hydrogen to burn and produce electricity during those difficult hours when there's very little wind and solar and when you'd otherwise have to use gas. We also found that as well as the technology, there will be a need for some policy changes to get to this zero carbon state. And the one that we focused on and was most material in our analysis is the introduction of €100 a tonne carbon price floor in the power sector. So this will be aligning the EU ETS level in the power sector with the non-EU ETS target of 100 euros a ton. And that is key as well to get the incentives aligned and to force the remaining gas fired generation off the system. So with those headlines, let me now just take you through the roadmap, the steps in our pathway to this zero carbon state for Ireland. And I'm going to take you step by step here and show you the reduction in emissions that we found in our study at each stage. Starting with the blue bar here, this is the existing 70 by 30 target and our latest view of the emissions level that implies. It's around 3.5 million tons in the power sector in 2030 under that less ambitious target. Then taking the measures to get to the 2 million tons of CO2 point removes about 1.7 million tons of emissions from the system. This is the increased build of renewables, getting to the 85% renewable power, and the implementation of zero carbon system services to get that element of the story in place. That gets us down to less than 2 million tons. In the next step, if we found that if one simply then continues to build renewable capacity in isolation, that does clearly reduce emissions further to some extent. So for example, here we go up to 94% renewable electricity, and we save another third of 1 million tons of CO2. However, doing that in isolation results in diminishing returns for emissions. What happens is that one ends up with an increasing amount of surplus generation and curtailment in periods with a lot of wind and solar, which is potentially not utilized, while periods that are most difficult to decarbonize when we don't have much wind and solar are not being fully addressed. And this is where we need to bring in these bulk energy storage solutions. And so you can see here, we've got 3 steps to the zero carbon state from that less than 2 million tons point. First of all, we applied the 100 euros a ton CO2 price, and that saves around 1/3 of 1 million tons from our figure. And so in isolation is quite an effective measure in getting the right incentives on the power market to reduce the reliance on fossil fuels in those difficult periods. Then the long duration storage deployment saves about another 0.3 million tons. The green hydrogen deployment, so that's around 1.3 gigawatts of hydrogen electrolyzers onto the system. That gives us about 500,000 tons saving. And if we add all of those measures together, and if we increase slightly the amount of renewables that we're building, that takes us in the final step to our zero carbon state. Next slide then, please, Justin. And there we have, that final step, 100% renewable power, 100% of the program for government capacity targets built, and we have the zero carbon outcome there. So that's the roadmap. What I'd like to do now is just take you through in a little bit more detail each of those phases to give you just a little bit more color on the measures that we included in the assumptions and some of the results coming out of our modeling. So first of all, phase 1, getting to that less than 2 million tons of CO2 level. And first, just giving you a sense of what the renewable contribution is to that and how that is made up by technology and what the level of build is that we're assuming here. So you can see in the chart, the renewable power, the RESI percentage for 3 different cases. First of all, the situation in 2020, the outturn, 43% renewable power in the Republic of Ireland. We then have the 70 by 30, the less ambitious target for 2030. And you see clearly an increase there, particularly in offshore wind and its contribution. And what we assume and what we find for the 85% case, the less than 2 million tons, is that we need an incremental scaling up of the offshore solar and onshore deployment. And the numbers we're talking about, so we have around 6.9 gigawatts of onshore wind in that less than 2 million tons case, just over 3 gigawatts of offshore wind, and around 3.5 gigawatts of solar PV. Those values are around 67% of the committed program for government capacity targets for onshore wind and offshore wind, just to put that in the context of those government targets. That's then the renewable generation side. What about the demand assumption? So we've taken these as far as possible from referenceable sources, and indeed our assumptions around demand and around the degree of flexible demand on the system are sourced from the 2019 Climate Action Plan in the case of the flexible demand, and the business as usual demand assumptions are EirGrid's own assumptions from their generation capacity statement. And the flexible demand that we have in the scenario here is quite material in helping to integrate the renewables that we have in the scenarios. And you can see here in our less than 2 million ton case, we assume build out of 1 million electric vehicles and deployment of around 600,000 heat pumps in Ireland by 2030. And that is aligned with the ambitions of the 2019 Climate Action Plan. I spoke a bit earlier about how key zero carbon system services are in unlocking this less than 2 million ton outcome. And what I've shown here is an illustration of why that is so important. And currently, with a reliance on gas-fired assets to provide system stability and system services, what that requires is that those gas-fired assets are usually running and are turned on, and they need to be turned on and running in order to be able to provide the level of response and flexibility and upward regulation that might be required. And they're turned on also to provide spinning machines that provide the inertia and stability to the grid. And on the left-hand side here, I'm showing the number of big thermal fossil fueled assets that need to be turned on under a situation without zero carbon system services. So this is the less ambitious 70 by 30 case. And we have a number of units in Northern Ireland and in the system as a whole, which must be maintained. So we have an overall minimum of 4 units or 2 units in Northern Ireland here. And what that does is it blocks out space on the system, which cannot then be taken up by renewable generation. So if you're turning on these power stations, you must turn off something else, and that may well be a renewable generator. What we have then on the right-hand side is the same chart of the number of min-gen units, as we call it, on the system, but this time under our less than 2 million ton case with zero carbon system services. And you can see that that min-gen level can fall to 0 because we are no longer reliant on the big fossil fuel spinning assets to provide that stability. And that creates significantly more space on the system for renewables and for wind and solar. And one of the other big benefits of that, not just creating space for renewables, is actually removing the emissions associated with keeping that gas-fired fossil-fueled fleet spinning to provide the services. And when we look at the emissions story, how we step down from today's level of emissions, 9-10 million tons of CO2 per year, down to the less ambitious 70 by 30 target, the 3.3 million tons there, and then down to the 2 million ton level that we're looking at here in phase 1, you can see that the biggest change between the 70 by 30 position and the less than 2 million tons is the removal of this set of emissions that we've shaded pink on the chart. And those pink emissions are associated with gas-fired assets providing system services. And so the shift to zero carbon system services eliminates that chunk of emissions. It's about 1.3 million tons of emissions per year, roughly. And that is one of the key savings then, alongside the additional renewables, that gets us down to that sub-million ton level. And then finally, for this first phase, I wanted to provide a little bit more color around that cost saving and this extraordinary message that this less than 2 million ton outcome actually can be delivered at a lower cost overall. And this chart shows us why that's the case. So this is showing the stack of additional costs and cost savings or benefits which are realized for this less than 2 million ton case versus the 70 by 30 target. Everything above the zero line here is an additional cost. Everything shaded in pink below the line is a benefit or a cost saving versus that point. So you can see that the additional cost here is mainly associated with items such as additional PSO support costs. So there will be a need to pay some PSO payments to some of the renewables that are built additionally in this scenario. There will be a need to pay for the new technologies which are required to provide zero carbon system services. So the DS3 costs here. But offset against that, there are two big savings. Number one is the fact that you save a lot of money not running the gas-fired plant to provide zero carbon system services. That's around 260 million euros a year saved on that basis. And then secondly, you have a big win for end consumers by building more renewables, which provides cheaper power, cheaper wholesale power, which is a benefit for all customer bills and provides another significant saving. So overall, giving 180 million euros a year net saving for end consumers. Okay, so that was phase one. Let me then show you in a little bit more detail how we get from phase one, less than 2 million tons, to that zero carbon result in the power sector. And a reminder that we're looking here at bulk energy storage, long duration storage and green hydrogen, and combining that with the policy intervention of 100 euros a ton carbon price. So let's look at those briefly in turn. First of all, that 100 euros a ton assumption, that saves us around 0.7 million tons of CO2 per year. And the key benefit of that 100 euros a ton carbon price is to provide the correct incentives in the power market to discourage generation which is emitting carbon, so that the gas-fired generation. We've assumed conservatively that that carbon price is common across both Ireland and its interconnected markets as well. Actually, if Ireland had a higher carbon price than its neighbours, the benefit for Irish emissions will be even greater than we're seeing in this scenario. But we conservatively didn't assume that was the case. Then looking at the long duration storage, that in isolation gives us around a 0.9 million ton of CO2 saving to contribute to our zero carbon pathway. What we assumed in that case was deployment of around 600 megawatts of long duration storage of around 60% round trip efficiency. We were not specific on the exact technology for that storage, but that could take a number of forms, and there are 5 or 6 or more technologies that would be viable to deploy and which are currently deployed and are feasible and in operation elsewhere globally. The role really of that storage is to flexibly absorb excess renewable generation when there's plenty of that available, and then to generate during those hours of the year when you would otherwise have to run a gas-fired plant. And once you get down to less than 2 million tons, that is really talking about 300, 400, 500 hours in the year maximum when you have significant gas-fired generation. So this is quite a small number of hours, in fact, which are contributing to the 2 million tons of emissions, which are the difficult hours that need to be addressed through this kind of storage technology. And then green hydrogen. So production of green hydrogen with electrolyzers during periods when there are low power prices, when there's a lot of renewable generation available, is very helpful. It generates a store of hydrogen that can then be utilized during those periods, difficult periods to displace gas. That can be done by burning hydrogen in a gas-fired power station that has been retrofitted. That is very feasible in terms of the technology. In fact, there are many other uses that could be envisaged for that green hydrogen outside of the power sector, which may have even greater emissions benefits. The usage of green hydrogen in industry or in transport or in heating. And those we haven't looked at directly in this study. It was out of scope, but there would be that wider benefit and story through this particular scenario. And then finally, combining all of those measures, so hydrogen, long duration storage, the carbon policy gets us to zero carbon. And that is a case where we have 60 terawatt hours of domestic demand across the island being met by 58 terawatt hours of wind and solar generation, some of that being shifted around by storage so that it's utilized and can be utilized in the right periods. Got a couple of terawatt hours of biomass waste and hydro generation, which is complementing the other renewables in that scenario, and about a couple of terawatt hours from hydrogen-fired power stations, which are helping in those most difficult hours. And then a final note just on the costs of getting to this zero carbon state. So we assessed the technology costs that would be incurred in deploying the solutions that we set out in our scenarios. And we're showing here what those technology costs look like in 2030. What I've done on the chart is show on the blue bar the actual technology costs in hundreds of millions per year. So we've got just over 50 million for long duration storage, 100 million for green hydrogen, and so on. With the dashed line, what I'm showing there is the cost saving to end consumers that emerged from the first phase of the study. So getting to less than 2 million tons saved at 180 million euros a year. And so you can see that many of these interventions in isolation are actually less costly than that saving to end consumers. And so there would still be a net saving overall in achieving the certain elements of these building blocks to zero carbon state in this scenario. To get to zero carbon and deploy all of these, there will be an additional cost to end consumers, which we show on the chart here. So finally, just to recap, we've shown that reducing power sector emissions in Ireland to less than 2 million tons of CO2 per year is very achievable by 2030. We need to do that through delivery of about 85% renewable electricity. And in doing so, we save end consumers money at around 180 million euros in 2030 versus the less ambitious 70% target. Then a zero carbon power system is very achievable for Ireland in the 2030s. That pathway requires investment in new technologies, such as long duration storage, green hydrogen, and it requires some policy changes, such as 100 euros a tonne carbon floor. And then finally, that pathway to zero carbon and really the the whole of our study is also underpinned by the message that it's crucial that the program for government renewable targets and the capacity that has been committed to there, the 8.2 gig of onshore wind, the 5 gigawatts of offshore, are kept and are delivered. And alongside that, a target that we've assumed for solar of around 5 gigawatts as well. And that is key. Delivering that capacity will be key to achieving the goals that we've set out in the scenarios here. So with that, let me kind of pause at that point, and I think we can open things up to Q&A and take any questions at this stage on the study.
Thanks very much, Mark. Like a really exciting presentation, I think, in terms of showing what we can and really must achieve over the next 10 to 15 years if we're to properly decarbonize our electricity and then subsequently our energy systems. Just to encourage people, I know there's a lot of people on the webinar with a great deal of experience in electricity generation, in development, in market trading. We'd really encourage people to submit questions through the Q&A function at the bottom of the screen. We want as many questions as possible. We want these research to be looked at and examined and discussed and analysed. So please do submit your questions. We do have one that's in already from Deputy Brian Ledden, who's chairperson of the Joint Oireachtas Committee on Environment and Climate Action. He's highlighting the fact they had the CRU into them yesterday, and they were highlighting the importance of gas as a transition fuel. And that was a really strong theme in their presentation. It's a really strong theme in the answers that they gave to members of the committee. And he goes on to say they seem to be more focused on decarbonising gas as a step towards net zero in the long run, rather than decarbonising energy as quickly as possible. My concern is we could end up locking in gas consumption for a very long time to come and not proceeding on a quick, rapid decarbonisation path like the one that is set out in the research. So maybe we'll throw that to yourself, Mark, first, and then maybe if Noel wants to come in as well.
Yeah. It's a great question, and I mean, I think, you know, the reality is there will be a role for gas over the coming years. So, you know, Ireland can't manage today without gas-fired capacity and generation, and it will need gas-fired generation to be on the system over the coming years. So, you know, there is a role there. I think there does need to be a recognition that to eliminate emissions from the power sector, you know, gas does need to, you know, be phased out in terms of the role that it has, and that's the vision and the pathway that we're setting out in the work. I do think that there is a viable pathway for gas-fired assets to remain relevant and useful, partly because it's very feasible to convert these assets to burn other fuels. And you know, we looked at hydrogen in the study, which we think is key. The retrofitting of gas-fired generation capacity to burn hydrogen at levels up to 100% is very feasible. And we've had a lot of conversations with OEMs to really understand the cost of that and the feasibility. And the message that we're getting back is that it is very feasible, and the cost is actually remarkably low to do that retrofitting. So this is not talking about abandoning the assets entirely. We will need assets that can burn fuels like hydrogen, and that will be an important part of the mix. It's just that, you know, on a pathway to getting to the kinds of emissions levels that the government is looking to target and that we've looked at in the study, you know, one simply can't have bulk usage of unabated gas in the power sector.
Noel, do you want to come in on that?
Yeah, I just echo everything that Mark has said, and maybe also I think we recognize more than anyone that the wind doesn't always blow and sun doesn't always shine, so there needs to be dispatchable firm generation that's there to pick up whenever renewables are not around. And at the moment, and for the next, say, the short term, that's going to be gas generation. But what we've set out in this study is that we can transition that to hydrogen-fired fuel. There's other options. There's ammonia as well. All the e-fuels are on the table here. We've just picked hydrogen in the study, but hydrogen is a vehicle that can be used to create more fuels for different purposes. The other thing I would say is that we've also looked at long duration storage technologies, which play a huge role in this study. I think we looked at 8-hour duration storage, about 640 megawatts of that mark. I was just reading even during the week that in Australia, they're rolling out over a gigawatt of this type of long duration 8-hour storage now in various parts of the Australian grid. So these technologies are live, they are happening in other jurisdictions. And what we really need to focus on is trying to bring about the route to market for these types of supporting technologies. The zero carbon system services and the demand side response and battery energy storage to try and help the system at times of high levels of renewables. And then the longer term dispatchable clean generation that isn't fossil gas that we can bring on the system later in the decade and certainly into the early 2030s.
Okay. So the next question is from Patrick Callan, who's bringing up the issue of interconnectors. So obviously we have the Celtic interconnector, we have Greenlink that are at some stages of their developing ahead, and these are interconnectors we hope to have delivered by the mid-2020s. Will that be enough? Will we need further interconnection than that? If people, maybe the two of you want to address that.
Yeah, so I think interconnection plays a really important role in making the system that we've set out, operable and functional. And so it does play an important role. So we've assumed that the interconnectors that are planned, Celtic, Greenlink, go ahead, and we have those in our scenarios. The thing that interconnection really helps with is the kind of hour by hour and day by day sort of fluctuation in weather patterns, for example, across island and interconnected markets. It helps when there are those periods when there are, imbalances and differences in the amount of wind and solar output in one market versus another. It helps smooth out those bumps. It plays a big contribution by doing that in improving the economics of renewables. So the fact that you are getting a better price in Ireland because the interconnectors are able to export during some periods when you have excess wind or excess solar in Ireland, and that other markets can take that power and utilize it and are actually decarbonizing their power systems thanks to that. So it's really important. I think what we did find in our study is that interconnectors alone are not the full answer for eliminating that final chunk of carbon emissions. And in fact, once you get down to that 2 million ton or just under point, adding more interconnection, it may have a lot of benefits elsewhere. It may make money, in fact, it may be financially viable to build another interconnector, but purely looking at emissions in Ireland, it has a diminishing return on that. And the reason for that is that, as I say, once you get down to that level, you're looking at bulk transfer of energy. This is about periods when there may be very little wind or solar for long periods of time, days at a time, versus times when there'll be an oversupply of renewables for an extended period, and it's shifting energy between those sorts of periods. And the problem is when you get a fundamental pattern of weather in Ireland, quite often that pattern is repeated and is the same in GB, in France, and in continental Europe. And actually, you're not able to solve that bulk energy transfer problem. And so that is why interconnectors don't contribute as much as you might think to that final elimination of emissions, although there are all sorts of other benefits that they bring, and we recognize that in the study.
I should say, Mark, I accidentally omitted the second part of Patrick's question, which is how much electricity do we find is being exported in the research that you've carried out?
Yeah. So we find in the zero carbon state that we have a small net export from Ireland to other markets, in fact. So it's a couple of terawatt hours a year in that scenario. It's a relatively balanced situation overall, but there is overall that slight net export to GB and France.
Could I just add to the answer as well? Just Mark, I think you've answered it brilliantly. Just to maybe call out one thing that we found, which I thought was incredibly interesting from an interconnector point of view, and that's the role of the carbon price. So if you look at the report, I think we've got some documentation on the usage of the various interconnectors in when we do not have a carbon price and when we do have a carbon price. And what you'll see is that there are times when there's almost a dead band of the interconnectors not being used at times without a carbon price. And the reason for that is the price of burning gas is setting the price in both, say, Ireland and GB or Ireland and France. So the incremental benefit of transferring power is lost a little because the prices are too similar. But when you put that carbon price there, we really see a higher level of usage of the interconnectors. So they're used much more often and they really begin to trade on carbon. So if we have low carbon in Ireland, we'll export to GB and France. If GB or France have lower carbon than they do in Ireland, then we'll import. So the choice which is almost made is, do we turn on a gas generator in Ireland to meet our power, or do we import renewables from other jurisdictions? And with the carbon price, we import much more often renewables from other jurisdictions instead of turning on gas in Ireland.
Okay, thanks, lads. Next one, perhaps one of the biggest question in decarbonising our electricity system over the next 10 years, can we develop the grid infrastructure at the pace that we need to achieve the kind of ambition that's set out in the Baringa research?
I can give this one a go, Mark, if you want, but I would just say that we always say that the biggest challenge to delivering our onshore and offshore capacity targets between now and 2030 will be grid development and the ability of the grid to move power from where it's generated to where it's needed in all of the cities in Ireland and Northern Ireland. So 100% we need grid development. I think core to the assumptions of this study is that critical infrastructure like the North-South interconnector are in place between now and 2030. We also have assumed the ability to transfer power from where it's generated to where it's required so that the grid is there and it is developed. We recognize that that's absolutely a challenge and that we might not get the entire grid that we need developed between now and 2030. But what we're finding is some of these alternative technologies that we're assessing, like green hydrogen, like long duration storage, if they're put at the right parts of the electricity grid, they can actually use renewable energy where it's generated, and there is no need to transfer that energy then across the country or towards, say, Dublin or Cork or Limerick. It's a way of minimizing oversupply or waste of renewable energy if you place these, say, longer term novel technologies that help us get to a zero carbon system in the right locations of the grid beside the renewables.
Okay. Might take the next question in three parts. It's quite a detailed one. So the first part is, how many climate years were studied in the research? So maybe, Mark, if you want to address that one first, and then we'll get to the next two parts after that.
Yeah. So the basis of the study took a kind of typical or P50 style year. So it was using weather patterns, I think from 2017. Alec will probably correct me if I've got that wrong. So that was the starting point. We then made sure that we assessed the viability of the system and the scenario under a more stressed situation than that. And I think in the question you sort of, or in one of the questions I can see here, you kind of refer to a kind of polar vortex style event. And we were very mindful of ensuring there was enough resilience in the scenario that it could cope with an extended beast from the east style event. And so what we did is we made sure that we had enough energy storage, enough hydrogen storage baked in to the zero carbon case to deal with that type of event. So we've got enough that Ireland can be essentially self-sufficient in terms of generation with very little renewable output. And we took as a benchmark, I think, events of, again, Alec will correct me if I get this wrong, but I think it was 2018 when there was one of those polar vortex, so beast from the east style events. And so we ensured we had 10 days worth of resiliency there. So there's quite a lot of hydrogen storage which is baked in. And that is what is then meeting that. There's the long duration storage, which helps significantly. The hydrogen, I think we've got 4.5, 5 terawatt hours of hydrogen storage baked in, and that is then key to ensuring that resilience during that sort of period. So we have stress tested it. Is that, that might be a 1 in 10 year, for example. What about a 1 in 20 year? What about a 1 in 50 year? One can always improve the resiliency of the system, but that comes with a cost. And so, that is a trade-off and a decision that would need to be made. Is it essential that the system can cope with a 1 in 20, 1 in 50 year and be completely zero carbon? Again, that's the kind of question and judgment that would need to be made. I think we're presenting a case that is zero carbon under an expected year and under a relatively extreme weather year as well. Actually, if you had to look at a 1 in 50 year and had to incur some emissions in that type of year, is that acceptable? Or actually, do we need to increase the amount of storage at a certain cost to eliminate even that event? Again, these trade-offs will need to be looked at, but that was the approach that we took for the scenarios in this study.
Thanks, Mark. And I think you've very efficiently answered the second part of the question about the polar vortex. So maybe just the last part of the question then was around retrofitting. And obviously that was a key part of the research, the importance of retrofitting existing gas generation to be able to burn with green hydrogen. The questioner is making the point that did we consider that a lot of this gas plant is actually approaching end of life within the next 10 years? And if we maybe want to comment on that.
Yeah. So we took a realistic view of plant lifetimes, and we already, we have assumptions, some of which are public and we're taking from AirGrid and the GCS, for example. There are known closures, which we, things that we know are going to come offline over the coming years. And so we took account of that. So I think we have a realistic assumption in the scenario of stuff that's going to come offline. And I think it's a good point that, this capacity that's coming to end of lifetime, it will come off the bars. And so, that's fine. We've ensured that there's enough dispatchable capacity in order to keep that system resilience within the scenario. So we're confident about that. I think the retrofitting point is key. And again, we might come back to this around, questions on gas-fired build, because I think that retrofitting theme is really key for gas, and ensuring that there is a pathway to retrofit. Now, in our study that we've done here, we think retrofitting for hydrogen is a key part of the solution. There are other ways you can retrofit. As Noel says, there are other electrofuels that could be used. You could retrofit with carbon capture and storage, and that is a potential solution. We think in this type of scenario where you have significant deployment of renewables as a key part of the solution, carbon capture and storage is maybe not the best suited technology, for the reason that it would be operating potentially in quite a peaky way. It would run for a limited number of hours per year. And typically CCS technology is not the best suited to that mode of operation, but it would certainly be a technology, on the table. But I think, and we may come on to this, I don't know, I'm reading ahead on the questions here, but I think key, if we are going to have new gas-fired assets deployed over the coming years, is to have that pathway to allow them to retrofit. And as I say, we think that is very technically possible, but it's quite an easy step, in our understanding, to ensure that can happen at the stage, particularly when you're specifying a new asset and a new plant. There are steps that can be made to make sure that it's spec'd in a way that allows that upgrade path over time. And that would seem to be a very sensible thing to be looking at in our view.
Thanks, Mark.
And maybe just to add one small thing, Justin, but just to back up what Mark is saying there, that it's absolutely critical that new plant that's developed is hydrogen ready or e-fuel ready. And we're seeing examples in other capacity auctions in jurisdictions in Europe where they're actually implementing that type of term in their T's and C's for the capacity auction, that if you want to be a new build, you need to be capable of operating in almost a zero carbon mode at a point in time.
Okay, 2 questions here from Project Daily. So first of all, were Article 13 costs included in the cost benefit analysis that was carried out? And then secondly, do you have any thoughts on, I suppose, uncertainty and forecast error as a barrier to getting zero carbon system services, you know, getting that over the line, so to speak, with long duration storage and hydrogen?
Yeah, I might defer to you on the first.
Yeah, maybe on the Article 13 part of it, and then Mark maybe on the forecast error issue.
Yeah, no problem. So for anyone that's unfamiliar, Article 13 is an article in the electricity regulation of the Clean Energy Package, and it stipulates that any redispatch of generation should be compensated for. So any curtailment or any constraint on the system should be compensated to the renewable generator. In our assessment, because we're operating a system with 100% SNSP and 0 megawatts of minimum generation on the grid, there is no curtailment, as we call it today. There is oversupply of renewables where there's too much renewables at points in time for the amount of electricity demand that we have available for. So there is no compensation in Article 13 for that type of curtailment or oversupply. And traditional curtailment that we have today on the system doesn't exist in a world where we can allow 100% SNSP and have 0 megawatts of min-gen. On constraints, I think I mentioned earlier that the electricity grid wasn't factored into this piece of analysis, other than to say it's vital for enabling it. So there are no constraints modeled specifically in the analysis in order to compensate. But what we've highlighted is a number of alternative solutions that can help minimize constraints. And we've highlighted that there is a cost saving to the consumer of 180 million euro per annum in our 2 million ton per year scenario. So there is an aspect there that if there remains constraints on the grid, that could be used as a form of compensation, but you would still have a cost saving to the consumer. It might also be worthwhile pointing out that in that 180 million euro per annum saving that the consumer makes in the less than 2 million ton scenario, we have factored into account the cost of developing the grid in order to enable our 2030 targets. So although the physical grid is not modeled, the actual cost of developing the grid is modeled. And we took the conservatively the most expensive scenario to develop the grid that EirGrid set out in the Shaping Our Electricity Future consultation. So even with the most expensive network build option, we're still finding an annual saving of 180 million euro per year to the consumer.
So Mark, do you want to maybe take the first part of the question?
So I guess around the balancing of the system, the forecast error. So there in our view would still be enough flexibility in the system to deal with that forecast error. So I'm not sure whether the question was focused on the kind of provision of enough system services and you know the grid services, or whether it's around the kind of energy balancing of the system. But I think on both counts, we'd be confident that there's enough flexibility in what we're putting out there in the scenario. I think we've got a substantial amount of battery storage on the system. We've got the interconnectors, which are very key for providing that flexibility. We have a lot of flexible demand, which is coming through partly from the EVs and heat pumps, partly from flexible demand sources elsewhere on the system, demand side response, some flexible industrial demand as well. And with all of that, there is quite a bit of flexibility for energy balancing. And as I say, I would be confident for system services that there's enough flexibility there to deal with any forecast errors that we would expect with that level of renewable build out. It's a great question. I mean, I think it is a very good question. You know, as we push towards these higher levels of renewables, there will be more forecast errors. And we know that forecasting has improved a lot over the past years, and it will continue to improve. I've no doubt about that. But there will be that forecasting issue. And so, ensuring that there is enough flex to deal with that was quite central to the scenarios that we put together.
Thanks, Mark. Next question is from Stephen Douglas, and also referring to the CRU presentation from yesterday to the committee, where they highlighted a belief that we needed at least 2 gigawatts of new gas generation over the next couple of years. And I suppose the question from Stephen, how would the addition of those 2 gigawatts, if they were developed, how would they affect the trajectory that's set out in the Baringa research?
Yeah. So, and I think, one of the keys, as we have said, I think, is to ensure that there's an upgrade pathway for those assets, and that would seem to be, prudent and logical, that you can switch fuels as and when that is, the right thing to do on the trajectory. I say we do think there's a need for gas-fired capacity in the near term, and indeed, in the scenario less than 2 million tons of CO2. We still have gas-fired generation there. So we still have 1.6 million tons of CO2 emissions. We still have gas-fired generation running for 500 hours in the year, and it's playing a role in that case. It clearly, it cannot play that kind of role if one's on a pathway to a zero carbon system, as we've set out. But it does, in that sense, play a transition role. I think there are a couple of challenges there. So one is that technical challenge, avoiding the stranding of those assets, and say that will be, I think, prudent to look at. Secondly, there is a piece around considering how those assets are going to be remunerated over time, because they will be earning less from pure energy production over time. There will be a shift towards, for example, a capacity market payment. And we, again, in the scenarios, have conservatively assumed a fairly high capacity market price, so 75 euros a kilowatt as a price coming through in the scenario that we've put out there. That compares to between 40 to 46 euros a kilowatt in all of the auctions to date in ICEM. So there is that piece for those asset developers and owners to consider, how they're going to be remunerated. But yeah, there will be a role there. There should be a sensible transition plan for both the developers and the government and the system.
Can I just make one addition to that, Justin? And it's maybe almost on our wish list, is if there is new gas generation developed, that firstly it's hydrogen ready or e-fuel ready, as Mark has said, but then secondly it's capable of operating at a very low minimum generation level and capable of cycling very often. So being able to switch on and off very quick and very often. Flexibility is critical to the system that we're looking at between now and 2030. So ensuring that the right parameters or design is there for those gas turbines will be really important. Maybe just in terms of, just to give people a sense of things, if you have say a typical 400 megawatt CCGT, if that operates at 200 megawatts, which would be a typical minimum generation level of a unit today, if that's operating for the entire year, that's 600 million, or it's 600,000 tons of CO2 into the system, just by one CCGT operating at half load for the entire year. So you really quickly build up emissions from CO2 if there is that minimum generation level remaining on the grid between now and 2030. So flexibility is critical for any new gas plant that is developed.
Thanks, Noel. And I might put the next question to yourself as well, from Jerry McAvilly, talking about the centrality of zero carbon system services. But what, in an Irish context, are the barriers from a policy, from a regulatory basis? What are the barriers to developing zero carbon system services to the point that it can meet the needs set out in Mark's research?
Yeah, thanks, Justin. Really good question. And I have to say that this is probably the part of the report that I'm most encouraged by, because the technology is there already. It's really proven, and all we need to do, as simple as it sounds, is get the market design right in order to get those units on the system. So if you want to break down system services into broadly 4 categories, so there's reserves, which are needed whenever there's a trip on the system, or a generator might have a fault. So you need power to be there to replace that power very quickly. The good news is that we're developing a lot of battery energy storage on the grid. So by this time next year, or by the end of 2022, we should have, broadly speaking, enough battery storage for system service reserve between now and 2030 already on the grid. So that's in development already. The second category is inertia. So this is the weight of the system, and it really helps to slow down the frequency fall if a trip occurs on the grid. And it was very encouraging again to see earlier this year the Commission for Regulation of Utilities put out a note to say that they would be procuring low or zero carbon inertia on the grid. So these can come from devices called synchronous condensers. They're being rolled out in the UK at the moment. We would probably need about 6 of these across the grid between now and 2030. In our analysis, we've estimated the cost of them between maybe 40 and 50 million. So 6 of those spaced out over time with a lifetime duration of 20 years is actually a relatively cheap solution to the consumer compared to turning on gas plant to provide you with inertia. They can also provide voltage support, which is the third category. So that's another solution there, and renewables can also provide that. And then the final category is ramping. So the ability to get power on the grid during, say, very harsh weather patterns or for unpredictable things on the system. And I think Mark has covered that already. The good thing about ramping is that to meet the requirement there, you just need the gas plant or the dispatchable plant to be on the system. It doesn't need to be generating. It doesn't need to be putting out emissions. It just needs to exist. So again, we can develop a system which is compliant there without the need to have gas running at all times. So first step, I guess, is to try and get those synchronous condensers on the system. So I think the CRU are going to run potentially an auction in the next 12, 18 months on that. And then the next step is to really reform system services and how they're paid for, which I think is going to come into play in 2024 and will be consulted on in the next few months. So those are probably the 2 critical next steps to deliver that future.
Thanks, Noel. Mark, do you want to come in there, or?
Really quick one. I think there will be a need to have a kind of investable, set of revenues for these assets. And I think just to emphasize that point, there's a revamp currently of the DS3 arrangements. I think it's encouraging that CRU has flagged that long-term contracts should be a feature of that to get perhaps the right technologies online. I just think that does need a lot of thought to make sure people can invest. People want to invest in these assets, and I think yes, that needs to be done with the best value for the end consumer. But what's coming out of our study is that there is such a huge win from going to zero carbon system services, this 270 million a year. That is vastly more than the cost of building the technologies that need to replace that. And so, there's a danger of being too overzealous in the sort of contracting approach, and yes, cutting costs, but ending up with nothing getting built. And I think, Ireland doesn't need to necessarily go down that route. The key thing is to get the stuff built, because then that's the end consumer benefit. And yeah, that just to emphasize that point that was coming out of what we'd done.
Thanks, Mark. Just to remind people, we're hoping to end this around 11:30, conscious of people's time for the day. There's 5 questions left open, and as you can see, I don't think there's very many simple questions. They all require fairly complicated answers. So just if you do have more questions that you'd like to get in, please do put them in the Q&A box, and we're going to try and get to as many of them as we possibly can. The next question is from Peter Brennan, suggesting that some of the new technologies outlined in the research are not convincing. I suspect that's very much in the zero carbon phase of the research rather than phase 1. And he's making the argument that renewables spread over a larger than local weather system is likely to be more feasible. And China has already started work on a supergrid with HVDC lines spread over 2,000 kilometers. So maybe to comment on that, the I suppose, how ready are some of the technologies we're talking about in the research, and whether renewables over a larger weather system actually might be a more efficient way of dealing with the problem?
Yeah, I think I would be probably a bit more confident about the readiness of the technologies. I think, and I actually would have shared the same reservation if I'd been talking probably 18 months ago around some of the technologies. But it's been extraordinary how much activity we've seen, certainly at Baringa, in these technologies and areas of the market elsewhere in Europe. So these are no longer exotic technologies that might happen in 10 or 20 years or 30 years time. They're happening right now. And I know that because we're working with developers elsewhere in Europe who are about to deploy these assets, particularly things like hydrogen electrolyzers. We're seeing a huge amount of activity in Europe around deployment of electrolyzers. So we have live projects we're working on in Germany, in Norway, and in Benelux, working with very, very credible developers and with proper capital behind them. Serious infrastructure funds are now putting a lot of capital behind power to X technologies, and electrolyzers are a key one. So really, I think all of the building blocks are there. Those investors and those developers are very confident in the technology, and I say it is happening already. So I think on that, I'm very confident. On the long duration storage, again, a lot of these technologies are not brand new. They're not experimental. They exist today. Things like liquid air energy storage, the molten salt storage has been deployed widely in Spain. We have compressed air energy storage. Pump storage, of course, is a very old technology across Europe. And so these are not, these are not wacky niche technologies. Again, they do need more development. Some of them have not been developed in Ireland, and that is absolutely true. And there does need to be more expertise and maturity and help to build them out. But they are not off-the-wall technologies that no one, has ever proven. And that was one of the central things of, the technologies that we fed into this scenario in the work is that, to make these as relevant and as immediate as possible, and not looking at, being saved by nuclear fusion or something like that in, 50 years' time. So maybe I'm overconfident, but I certainly more confidence in those technologies from what I see in the market.
And what do you think about the second part of the suggestion from Peter, that actually we should be looking more at renewables spread over a much larger area, having a super grid that could move power from very different parts of the world, move it very, very quickly?
It's a fantastic concept, I think, and I think partly Ireland, in a maybe not quite as extreme a way, is going to benefit from that sort of effect with offshore. So offshore wind will have that kind of effect. It's accessing different weather patterns. It's accessing a more consistent supply of wind, and it will be geographically in slightly different areas as well in the island. So that in some sense helps. I do think the concept is a good concept. And I think it will work in some parts of the world. I think getting the transmission infrastructure and technology is key, and there are a lot of interesting developments around super efficient grid infrastructure that could make that sort of concept even more feasible. So I think it's a very interesting concept, and I think Ireland is probably going to take advantage of that to some extent within what we've set out in the scenario.
Thanks, Mark. Next question from Patrick Calnan. In terms of DS3 increased costs, has the report considered the overall returns over the lifetime of the assets to ensure that they're built?
Yeah, so really good question. We set out the kind of economics of the new technologies that would need to be built, and we factored in a reasonable return on that investment. It was actually quite a conservative return in terms of it being relatively generous. So I think we included a 12% return on some of the technologies such as synchronous compensators that we were deploying. And then we looked at the capital costs, the fixed costs, the variable costs of those assets, that 12% return that will be required in that assumption. And then we spread that over a reasonable lifetime of the asset. So we came up with an annuitized cost, which is what is then coming through in that 2030 cost stack. So that cost will be repeated for a number of years, of course, over the economic lifetime of the asset, as you'd expect. But yeah, that was the kind of approach we took there. So 12% return roughly for that kind of new technology, which is is a little bit higher than we would assume certainly for renewables these days, and for standard battery storage that will be somewhat lower than that. But reflecting that these are new technologies to Ireland, and there may be a little bit more perceived risk around that. So yeah, we factored in a slightly more generous WACC on that.
Next question is Noel mentioned this a little bit earlier on, that we were talking about 6 synchronous condensers, I think, in the research. And this question is about, is there a detailed breakdown of the technology that we refer, when we talk about zero carbon system services, what exactly are we talking about and how much of it are we talking about? Is that in the research?
It is. Sorry, no.
No, I was just going to say, like, it's there. There's a really detailed set of tables right at the end of the report, setting out exactly the amount of battery storage, the duration of battery storage, the amount of demand side response, and the duration of demand side response. I think our assumption in the report has been that there's enough synchronous condensers to cover the inertia requirement on the grid. So that's between 5 and 6. What's probably not in the report is the location of them, Mark, if I'm right in saying that. Again, if you place them on the grid in the right position, they can really help in terms of things like voltage support and really minimizing the need to develop new grid infrastructure as well. So I think a good rule of thumb is look where there's thermal assets on the system today and try and site your synchronous condensers somewhere near them. So I think Dublin, Cork, Moneypoint, the Midlands, Belfast, and probably the west of Northern Ireland would be 6 brilliant locations to have synchronous condensers if you were looking to develop them on the grid today.
Thanks, Noel. Mark, do you want to come in on this as well?
So yeah, I mean, just to kind of reinforce. So there's a detailed annex in the report. So we've got a breakdown of the technology kind of assumptions that are in there. So hopefully that will give all the detail that you need on the breakdown. If you do need more detail, then do reach out to one of us, and we're happy to provide more granular detail if that's not already covered in the report. But I suspect that will cover what you need.
Just a reminder, we will be sending out the slides from the presentation today, a link to the video and a copy of the report again to any registered attendees, but please do come back to us if there's any questions or queries that you have. Next question from James Ryan. I might read out, it's quite a detailed one. Can you discuss the operability challenges of the less than 2 million tons system? Forecast errors force operators to act defensively, requiring more dispatchable capacity than might otherwise be assumed to be needed. He then goes on to say, there's no system in the world currently operating with the level of inverter-based technology that is assumed in this report, and that there is a missing technology to enable a system to swap between all inverter-based technology and a mix of inverters and synchronous generation. So I don't know which one of you two gentlemen wants to take the first crack at that one.
I can have a cut at it, Mark, and then you can come in.
It worries me that there was an awkward pause there.
No, you're fine. No, cheers, James. I think on the forecast errors and the ramping, absolutely. I think we might have covered that already. It's just that there is an assumption that there is a base load capability of synchronous units there in order to cover off any forecast or ramping issues that exist, and that's complemented then by the battery energy storage, significant levels of demand side response, a lot of domestic flexibility in terms of EVs, heat pumps, and the long duration storage and electrolyzers can play a role there also in the zero carbon world. In terms of the missing technology, I think that we are still operating a synchronous system, so the synchronous condensers are there. So there is synchronism happening. There's a lot of inverter-based technology. There's no doubt about that. I think the studies need to be done by EirGrid, by ESP networks by Sony, by NIEN, to operate the grid at 95 to 100% SNSP. There's no doubt about that. I think what we've set out in this report is the benefits of being able to do so and to make that leap from the 95% to the 100% SNSP, and more critically, actually, to reduce the level of minimum generation needed from the fossil fuel units off the system. So if you have the right the right synchronous condensers in the right areas, if you potentially have things like grid forming inverters from your renewables, which again are being rolled out in other jurisdictions, but they're not in Ireland yet, I think that leap can be made. And I would see zero carbon system services as being one of the more immediately achievable things that we've put forward in this report.
Okay, Mark?
I was just going to add that I guess EirGrid is already, pretty ambitious in what it's set out in its Shaping Our Electricity Future document, and it's targeting already operating the system with a lot of these technologies and with almost all the constraints removed. So 95% SNSP by 2030. That's to hit the 70% target. So EirGrid's already signaled that operating at 100% and totally removing some of these constraints is feasible. Again, that gave us, confidence in a sense that, this was feasible. And I think, again, it's not that far removed from what EirGrid is already envisaging for 2030.
Okay. We've 10 minutes and 2 questions left. So if anybody else wants to come in with an additional question, I think now would be probably a good time, and we'll try and draw a line under any additional questions after that. The first one, are there any examples of hydrogen production from offshore wind that are commercially operating at the moment anywhere in the world? So
yeah, great question. So I don't believe there is anything directly connected to offshore which is commercially operating at the moment. So there are a couple of pilot projects that will be operational quite soon. I think there's one in the North Sea that was due 2021, so later this year. So over the next 12 months or so, we will see some projects emerging. The technology itself is pretty well proven. So electrolyzer technology, I think one of the key things is ensuring you have flexibility in the electrolyzers, and so deploying the right technology is quite important. And there are, as I understand it, two main types of electrolyzer. You have the slightly older alkaline technology, and then you have the PEM, so-called PEM technology, which is more flexible and is able to flex to load a little bit more readily. And so, selecting the right technology will be key. But yeah, we will see, I think, over the next 12, 24 months, a number of commercial or pilot projects coming through on offshore and hydrogen.
Yeah, I think there's a number of our offshore wind energy developer members who are also considering hydrogen as a fairly key part of their mix over the next 5 to 10 years. Just to bring in this next question on biomass. So biomass was obviously part of the mix in the 70 by 30 research that Baringa produced a couple of years ago, and I think was really important in driving the debate forward in Ireland. It's not part of this research. It's not part of the technology mix. Could you maybe explain why and what was the thinking behind that?
Yeah, so we do have some biomass on the system in the scenarios. So it is part of the mix that we're putting forward. There was really the simple reason why we didn't include more within the power sector is that we felt that with the necessarily constrained volume of biomass that could be likely sourced, there may be a bigger impact on an emissions basis of playing that into the heating sector, for example, or industry directly, or even transport in the case of biomethane. But industry and heat, which are, clearly have their own significant challenges on decarbonisation, we had a sense that there may be more value there, so we didn't include it. I mean, I think there is a potential role, there's no doubt about that, for biomass. So, I wouldn't be surprised to see some more contribution from biomass in the mix. And I think overall that helps the picture. If there is biomass which is available to go into the power sector, that's the right home for it, then that really would make achieving what we've set out here a little bit easier, given that's a dispatchable asset. It's, you know, it's got flexibility. So, you know, we, in a sense, we're making life a bit difficult for ourselves by not allowing a little bit of that in the scenarios. But that was the thinking and rationale behind doing that.
Thanks, Mark. And the last question from Reen Hughes, there hasn't been much mention of port development. Was this included in the study? And I think it might be slightly out of the context or the scope of this piece of research, but it is something that we looked at in Harnessing Our Potential, which was a major piece of research in the offshore supply chain that was published last year. So Noel, I might throw this one to yourself. How important is port development in getting the infrastructure for offshore wind energy? How important is it to try and achieve the targets and the generation that's set out in the Baringa research?
Yeah, massively important. So it's you're right, Justin. It isn't a factor that was included in this analysis. This analysis assumed that the offshore wind could be developed and built, but critical to that is the supply chain and ensuring that we have the infrastructure in Ireland to be able to develop those offshore wind farms. So Justin mentioned last year, I think around May, we published Harnessing Our Potential, which was a report that we did with the Carbon Trust on the offshore supply chain that would be required in Ireland. We looked at the investment that would be needed in areas like ports, enterprise hubs, education, to try and ensure that we have the workforce and capability to grab and capture as much of the value for offshore wind as possible for Ireland. What we really need to see very soon is investment in perhaps strategic ports on the East Coast, South Coast and West Coast in order to be able to deliver the offshore wind projects that we need between now and 2030. The majority of offshore wind projects between now and 2030 will be likely on the east and south coast, with the west coast playing a role perhaps in 2030 and certainly into the 2030s. So getting that investment and getting those ports developed is not quick. We need to make that decision now, and we need to make that investment now in order to have those ports ready by the middle of the decade and the second half of the decade to be able to roll out and deliver these projects for 2030.
Okay. Well, gentlemen, you've answered all of the questions, which I can only assume means that everybody else still watching the webinar agrees with us completely. But if you don't, and if you have other questions, or if there's criticisms or ideas or suggestions that you have, please do get in touch with us. We do want this to be a living piece of research. We want this to be stimulating debate. We want people to be thinking about it, challenging it, interrogating it. So please do come back to us when we send the email out with the report, the slides, the webinar, and all the rest of it. A couple of quick thank yous. First of all, obviously, thanks to our participants today. Thanks to Noel for joining us, and also to Mark and to the team at Baringa and to Alec for all of the research and all of the work that they did to put together what is an enormous piece of research, I think, and I think a really valuable contribution to the debate about how we decarbonise the energy system in Ireland. Thanks as well to Mark and Jeanette and the team at GreenTech SkillNet for of their support in terms of organising this webinar and I suppose the work that we're doing in the research area as well. And thank you who joined us today, and thank you for giving us so much of your time. And thank you particularly to everybody who put forward a question. I think there were some really excellent ones and some really challenging questions, and those are the kind of questions we want more of. So thank you very much, and I hope to see you again soon at another Wind Energy Ireland webinar. Thank you very much.
Thank you.
Thanks, everyone.